So welcome again. In the last lecture, we have defined order of an element in a group. So in this lecture, we'll see some examples and we'll prove some properties related to order of an element. So let us proceed. Okay. So again, recall, what do we mean by order of an element in a group? So if G is a group, G is a group, and if X is an element in G, then the smallest n in N such that x to the power n is identity is the order of x. Okay. Okay. So example, examples number one. Let G equal to Z. Now, if you take your x equal to 1, then for all integer uh, k, for all natural number, let's see, k, what is x to the power k? X to the power k is 1 plus 1 plus, because it's an additive group of integers. Remember, z means actually z plus. So x to the power k means x plus x plus x plus k times. So it is 1 plus 1 plus 1 k times. K times. So can it be equal to the identity? What is the identity? The identity element is 0. This is never 0. This is never equal to 0. So the order of x is not finite, it is infinite. The second example, suppose our group is GL2R. So my G is GL2R. And suppose A is a matrix 1, 1, 0, 1. Then what will be the order of this element A? Take any natural number K. So see, for all natural number K, what will be A to the power K? If you calculate, this is not difficult. If you go on multiplying, you will find that your A to the power K is actually 1 K 0 1. And so this is also not going to be the identity element. What is identity element? Identity element is 1 0 0 1. So whatever K you choose, this A to the power K is never identity. So the order of A is also not finite. Order of A is infinite. But instead of this, if I take my B in GL2R, if I take my B is equal to 0, 1, 0, sorry, it was again some problem. So let me write, say 0, 1, 1, 0. Okay, then what is B square? B square is 0, 1, 1, 0, 0, 1, 1, 0 equal to 0, 1, 0, 0, 0, 1. So identity, right? And 2 is the least natural number definitely, for which B square is identity, and therefore I can say the order of an element is denoted by O of that element. So order of B is 2, right? Okay. But if you are working with a finite group, suppose I am working with a finite group, say Z7, addition modulo 7. Then let us find the order of any element. Say let us find the order of element 5. 5 means actually equivalence class of 5. So I am writing simply 5. That is understood that it is equivalence class of 5 with respect to modulo 7. Okay. So what will be 5 square? What is 5 square? 5 square means, first of all, 5 is not the identity element. That is 5 is not equal to 0. What is 5 square? 5 square is 5 addition modulo 7, 5. What is that? That is equal to 5. 5 plus 5, sorry. 5 plus 5 is 10. 10 by 7, so 3 is remainder. So this is 3. What will be 5 cube? 5 cube is 5 addition modulo 7, 5 addition modulo 7, 5. That is 3 addition modulo 7, 5. What is that? 1. What is 5 to the power 4? 5 to the power 4 is 5 addition modulo 7, 5 addition modulo 7, 5 addition modulo 7, 5. So it is how much? 3 addition modulo 7, 3. So this is 6. Similarly, what will be 5 to the power 5? 5 to the power 5 is 6 addition modulo 7, 5. What is that? That is 4. And what is 5 to the power 6? It is 4 addition modulo 7, 5. That is 2. And what is 5 to the power 7? It is 2 addition modulo 5, that is equal to 0. So 7 is the least positive integer for which 5 to the power 7 is equal to 0, and therefore we can say order of 5 is equal to 7 in Z7. Okay, in this group. Okay, so I hope that you have understood what actually order is, order of an element is. Now let us prove a result regarding order of an element. So let's see. So result, let G be a group and let X belong to G be of finite order, say k, if x to the power t is equal to identity for some t is in z, then t equal to kr for some r belong to z. Okay, so that means if you know that an element has a finite order, say k, then for any integer for which x to the power t is identity, that integer is actually a multiple of the order of the element. That is to be proved. So proof. If x equal to identity, then we are trivially done. Then what will be k? K will be equal to 1 because identity to the power 1 is identity. And t equal to 1 into t, right? So thus we are done. Let us assume that x is not identity. And let us assume t belong to z be such that x to the power t is equal to identity. Now apply division algorithm. What does division algorithm say? Division algorithm says that you give me any integer, you give me two integers, rather I should say. I can produce two unique integers. Suppose you have given me p and q. I can produce two unique integers m and n such that p equal to qn plus m, where m is definitely non-negative and it must be less than the second element, that is q. Now I want to apply division algorithm. So I have two integers t and k. By division algorithm, there exist unique PQ such that T equal to KQ plus P, where 0 less than P, strictly less than K. Okay, fine. Let P not equal to 0. If P equal to 0, then we are done. Then x to the power t is equal to x to the power kq plus p equal to x to the power k to the power q plus x to the power p. But k is the order of the element, so x to the power k is identity. So it is identity to the power q plus x to the power p equal to x to the power p. Correct? But you know that x to the power t is identity. So this is equal to identity. But is it possible? If this is possible, actually this means, therefore, you are saying that k, that is the order of the element, that is less than equal to p. Because k is the least positive integer for which x to the power k is identity. You have proved p is an integer for which x to the power p is identity. So k should be less than equal to p. But that is false. That cannot be, because I know that p should be less than k. So this is not possible. Hence, p should be equal to 0, and so t equal to kq. So we are done. Q equal to r. Okay? Okay, fine. Let us prove another result. Some important results. Let G be a group then the following holds. Number 1, if an element x belongs to G is of infinite order, then x to the power k is not equal to x to the power L for k not equal to L in Z. That is quite obvious. We'll see that if order of x is equal to KL for an element x belongs to G, then order of x to the power k is equal to L. Number 3, order of x is equal to order of x inverse for every element x in G. And number 4, if x is an element in G, then order of x is equal to order of Gx G inverse for all G belong to G. So let us prove one by one. Proof. number 1. What to prove? See, in number 1, we have to prove that if an element x is of infinite order, then x to the power k equal to x to the power l for all k not equal to l in Z. Suppose it is wrong. Suppose there exist k not equal to L in Z such that x to the power k equal to x to the power L. This implies x to the power k minus L is equal to identity. And this will imply order of x is less than equal to, or okay, I don't know k is bigger or L is bigger, but at least we can say that order of x is finite. So this implies order of x is finite. So that is a contradiction. You have assumed order of k is infinite. So this is proved. Therefore, x to the power k cannot be equal to x to the power L for k not equal to L in Z. Okay, fine. Next, number 2. Let order of x is equal to KL. Therefore, x to the power KL is equal to identity. If we apply generalized associative property, then we can prove that x to the power KL is nothing but x to the power k of L. This is equal to identity. Okay. Now, what does it mean? It means that order of x to the power k is less than equal to L, right? Okay. Of course, these are natural numbers that I have not said. Fine. Suppose it is strictly less than L. Is it possible? Suppose order of x to the power k is equal to t, which is strictly less than. This implies x to the power k to the power t is equal to x to the power kt. That is equal to identity. And this implies order of x is less than equal to kt, and kt is strictly less than kl. So is it possible? No, this is a contradiction because we know that order of x equal to kl. So this is a contradiction. Therefore, order of x to the power k must be equal to L. Okay, now let us prove that order of x is equal to order of x inverse. Number 3, let order of x is equal to n and say order of x inverse is equal to m. Now order of x is equal to n implies x to the power n is identity. This implies x to the power n inverse is identity. This implies x to the power minus 1 whole to the power n is identity. This implies order of x to the power minus 1 is less than equal to n. And this implies m less than equal to n. Now interchange the role of m and n like this. Order of x to the power minus 1 is m. This implies to the power m is identity, implies x to the power minus m is identity, implies x to the power minus m inverse is identity, implies x to the power m is identity, and this implies order of x is less than equal to m, but order of x is n, so n is less than equal to m. So it proves, therefore, order of x is equal to order of x to the power minus 1. That is order of x equal to order of x inverse. Okay. Okay, let us prove the last one, that is number 4. We have to prove that order of x equal to order of gx g inverse for all g. Okay. Okay. Okay, before that, one particular thing. If order of x is infinite, then what happens? We have proved, assuming that both are finite. You see, suppose order of x is infinite. If order of x is infinite, then how to show order of x inverse is infinite? You see, from this paragraph, if order of x is infinite, and if you assume order of then for then if order of this is finite, then to the power order of x inverse is identity. This implies x to the power minus order of this is identity. But this is a contradiction because this is a finite quantity and it proves that order of x is finite. So therefore, order of x inverse is infinite as well. And similarly, other part. Please complete the proof by giving that statement that if order of x inverse is infinite, then order of x is also infinite. Now let us prove the last statement. To prove the last statement, first of all, we claim let x comma g be two elements in G, we claim that Gx G inverse to the power k equal to Gx to the power k G inverse for all k natural numbers greater than equal to 2. K equal to 1, it is obvious. Let us prove it for k equal to 2. Let k equal to 2. So Gx G inverse square equal to Gx G inverse into Gx G inverse. This is equal to G x G inverse G x G inverse equal to G x, and G inverse is identity, so it is x square and G inverse. G inverse G is identity. Okay, so we are done. If k equal to 2, we are done. Now let the result be true for k, and we'll prove it for k minus k plus 1. Okay. Okay. Let it be true for k greater than equal to 2. Then Gx G inverse to the power k plus 1 equal to Gx G inverse to the power k Gx G inverse equal to Gx to the power k G inverse into Gx G inverse equal to, what is this? This how I have written, because already I have assumed that if k is greater than equal to 2, this is true. Now this is G x to the power k G inverse G x G inverse equal to G x to the power k plus 1 G inverse. So I am done. That means if you assume it to be true for k greater than equal to 2, then it must be true for k plus 1 also. Then I am done. Therefore, G x G inverse to the power k is equal to G k G inverse x to the power k G inverse for all k greater than equal to 2. That is proved by induction. Now we have to prove our claim. What was our claim? Our claim was that order of x and order of xg, x inverse are same. So let order of x is finite, be finite, and suppose it is equal to k. Therefore, Gx G inverse to the power k, just now we have proved that it is G x to the power k G inverse but order of x is k, so it is G inverse is identity. So therefore, it proves that order of G inverse is less than equal to k. Okay. Now suppose order of G inverse, because this is finite quantity, if you assume it to be finite, then it is proved that order of G inverse is also finite. Let order of G inverse is equal to L. Okay. Then X can be written as G inverse G inverse G. So if you apply whatever we have proved just now, x to the power L will be what? It will be G inverse G inverse to the power L G, replacing G by G inverse, equal to G inverse. And what is G inverse whole to the power L? It is Gx to the power L G inverse G equal to G inverse G x to the power L okay, that is not required. That is also not required because we have assumed that order of this is L. Okay, fine. So no need to write this. So it is equal to G inverse EG, that is identity. So it proves that order of X is less than equal to L. So once you have proved that order of G inverse is less than equal to K, and now you have proved that this actually implies that K less than equal to order of G inverse. So they must be same. Okay. Now, suppose order of X is infinite. One thing from this proof, what we have understood that G x to the power K G inverse is equal to identity. We have this we have derived identity if and only if x to the power K is equal to identity, right? From the above thing. So if you say, and this actually means that is G inverse whole to the power K, because this Gx to the power K G inverse is same as G inverse whole to the power K. This is equal to identity if and only if x to the power K equal to identity. Thus, if order of any one of them, any one of x and G inverse is infinite, the order of the other is also infinite. Actually, here we have proved that order of x equal to order of Gx G inverse, provided both order are finite. So now ultimately we proved, hence order of x equal to order of Gx G inverse, and this proves our claim. So what we have proved in this lecture, if we recall, we'll find that we have seen some examples to understand what order is actually. So we have seen that in a group, if there exists a smallest natural number for which an element to the power that natural number is identity, then that smallest natural number is called order of the element, that particular element. We have also seen that order of an element need not be finite always. There need not exist any smallest natural number satisfying that. In that case, we say that order of the element is infinite. We have seen some examples of elements of infinite order in many groups. We have seen examples of elements of group having finite order also. If the group is finite, automatically order of every element will be finite. That we'll see. But we have seen an example, of course, Z7. And then we have proved the result first, that if order of an element is finite, then for any integer t, if x to the power t is identity, then t must be a multiple of order of x. And then we proved results having 4 parts, that if order of x is of infinite order, then if k and l are not equal, then x to the power k cannot be equal to x to the power l. And if order of x is kl, k and l are natural numbers, then order of x to the power k is equal to l. Order of x and order of x inverse are same. Not only that, order of x and order of Gx G inverse are also same for every element G in a group G. Okay, so this is all about this lecture. Thanks. Please go through it. If you have any doubt, please let me know. Okay, thank you.